Yes, I apologize. It's a very, very long title, so I'm not going to read it and waste my time. We'll just call it Microbes That Eat Rock Underground. This is not my title. My advisor likes to be very descriptive. So we'll move on. So just as a general introduction, we all know that the Earth is, kind of composed of igneous rocks that are rich in reduced compounds, such as reduced iron. And this iron is essentially a very vast energy reservoir for microorganisms. And so there's been a lot of work recently really focusing on the ability of microorganisms to use structural iron in silicate minerals as an energy source. And I've just highlighted two studies here that are kind of basis of this work where, let's see, aha, my finger's in the right spot. Look at this. I can follow directions. So in this study by Bailey and, so Alexis Templeton here, this is actually an isolate that I have that I'm trying to play with a little bit. They've demonstrated this is actually an amorphous. It's not a crystalline mineral, but definitely increased cell densities. So they demonstrated in both of these cases colonization of either an amorphous or a crystalline iron-bearing compound. And this is great work, but what it doesn't really tell us is anything about the mineralogy or about what's happening to the mineral or how is this actually working. Yes, we've demonstrated that we do definitely see colonization by microorganisms, but we have to go a step further beyond that and actually synthesize this and do a more coherent picture. We have to look at more than just cell numbers, right? So in this study, this is out of my group at Madison, but before my time. So this predates me. But this is really a fundamental component to what I want to do. And in addition to just tracking, yes, cells are increasing, that's good, your cells are growing. But we're also tracking a loss of iron from the mineral. So iron, that's good, the iron's going away. And this is a nitrate reducing condition, so you're losing nitrate. So synthesizing all of these things together, not only do we just see higher cell densities, but we also see loss of iron from the mineral structure. And then by really interrogating the mineral, so this is the mineral biotite, we're actually seeing mineralogical changes in the presence of these bacteria. And you can track that. The increase in potassium in the culture, that's expulsion of your interlayer cations due to the oxidation of the structural iron in this mineral. So that's another piece of evidence that we're having mineralogical alteration in the presence of these bacteria. So this is really cool. And based on all of that evidence, we have this proposed mechanism behind this structural oxidation. In a very simple scenario, you could just imagine you have some mineral abiotically dissolving, right? Just boop, the reduced iron pops out of the mineral through a abiotic process. The micro says, yum, that's delicious, and then, oxidizes it. However, this previous experiment was done under circumneutral pH, and these minerals are not, the dissolution is not that rapid. They just sit there. So you could think of another situation, which is our kind of favored hypothesis, is that this is a direct enzymatic attack on the mineral surface. And this is not that far-fetched. We see this in iron reducers. You can think everybody's favorite iron reducer, Geobacter, right? You can think they have this, it's a direct enzymatic attack, right? These outer membrane proteins, that's what the OMP is here, that engage in the shuttling of electrons. So these are genomically encoded outer membrane proteins that are involved in the extracellular electron transport of iron. So this is the idea. Based on the evidence, we don't think these are abiotic processes, just abiotic dissolution coupled to iron oxidation. We think that it's a direct enzymatic attack. So this, of course, I do have to give my nod to astrobiology, right? So there's iron on Mars or something. Someone tells me that. So I've heard this rumor that there's iron on Mars. So this really cool paper here, just theoretically crunching the numbers, based on iron-based lithotrophy alone could have given us just approximately 20 grams per centimeter of biota over the course of Martian history, just based on the alteration of the iron-bearing mineral phases. So cool, right? So there's your relevance. But what we really want to do is test this in an actual field setting, right? So these laboratory studies and theoretical calculations are great, but we want to take it to, quote, nature, right? Let's go to nature. And I tell you, this was terrible. This was a terrible place to go. So I just got back, so I don't really have a lot of really cool data for you. But so we went to the Luquillo Mountains, or I went to the Luquillo Mountains in Puerto Rico. This is a critical zone observatory. And I know it's not a basalt, so please don't give me grief about that, okay? I realize this is not a basalt. This is a granodiorite. But it does have an appreciable weight percent of iron-bearing phases, such as biotite and hornblende. The really, really remarkable thing about this is how fast this thing is weathering. This is one of the most rapid weathering rates for a granitic material that's ever been recorded. This thing, the saprolite advance rate on this thing is on the order of 58 meters per million years. If you aren't familiar with weathering rates, that's an order of magnitude faster than the global average for a granitic system. And that's partially attributed to climatological variables, high temperature, high precipitation. This is a rainforest, after all, and as well as topography. But what you see, so it's weathering typical granite weathers like an onion skin spheroidically, and that's driven by the initial oxidation of the structural iron in biotite, and that leads to expansion of the D layer, so you get eventually fracturing, and then it's just a runaway process from there. But the initial step in this weathering is actually the oxidation of biotite, and then the rapid dissolution of the other iron-bearing phase, which is hornblende. So there's evidence that not only is this weathering very quickly, because it is, that microbes may be playing a role here, and this was essentially this 2005 paper. It was my Bible. So my entire work thus far is based on this kind of theoretical paper that maybe it's microbes. So what you're looking at is you see a loss of iron, so at depth. So this is let me back up. This is a superficial expression of what's happening underground. There's a recent landslide that exposed this normally. This is the saprolite bedrock interface is variable, but usually 5 to 8 meters depth. Should clarify. So this is at 5 meters, and then you see up through the saprolite, you see a depletion in iron. But what's really interesting is the cell count. So you have high cell densities at the surface, right? Okay, ooh, no big deal. And then you move down through the saprolite, you see this wiggle right here. I'll talk about that in just a second. But down again right here, so this is DNA counts, or DNA yield and direct counts. You start getting close to that rock, and you start seeing increased cell densities again. And these also have those little IBART, they're these geochemical tests, or biochemical tests for iron-related bacteria, how much stock you put into those. I'm not really sure, but taken together, this suggests that we have this conceptual model. Again, superficial expression of a subsurface process. This is a road cut. So this would be a core stone of the granodiorite. It's fractured because it was blasted with dynamite to make the road. But on top of it, you see the dinner plate stacked like rhinelets that are associated with the spheroid weathering. And then conceptually, so you have the bedrock, you have your rhinelet zone, and then your saprolite. So you can calculate the amount of biomass based on the free energy, and you can actually produce more cells at depth based on the upward flux of iron out of the rock than you can by the downward flux of carbon. So these are probably lithotrophs. So that's our hypothesis, is that through a direct enzymatic attack on the mineral surface, these microbes, these iron-oxidizing bacteria, are going to play a direct role in the rapid weathering of this quartz diorite. And metagenomic characterization of the in situ community is going to lend insight into this process. And we're also going to do some culturing to determine or to show selective colonization of the mineral surfaces. So this is the real rock. This one doesn't exist anymore. I crusted it with the old S-wing and threw it in some artificial groundwater. But so we took 3 cores. Again, the saprolite is variable in thickness. Basically, did this with a hand auger until you couldn't go anymore. And so, again, it's variable. But we sampled periodically down through the saprolite profile aseptically for microbiologic and genomic analysis. And what I'm doing right now is I set up enrichment cultures. This is a very wordy slide. I realize that. But we're using an artificial groundwater. So they get water, they get minerals, and they get CO2. That is it. That's all they have in nature, so that's all they're getting here. And so I actually used the parent material, the granodiorite, and because it's a very trendy thing to do, I did a deconstructed menu where I took the granodiorite and split it into its components, the hornblende, a biotite, albite, quartz, and this muscovite's a control for another reason. But so we're just monitoring them over time. They're lithotrophs, they grow slowly. I don't have any evidence that they're growing at all right now, but it's only been maybe a month. So at the end of the day, we are going to go after them. And hopefully they're going to grow, right? Cheer them on, say, please grow, please grow. Okay. And then also the really kind of cool part about this, the part that I hope to tell you more about later, is the metagenomics. And what we want to do, remember this direct enzymatic attack, these are genomically encoded extracellular electron transport genes. And so we know how to find these, right? These diagrams are from Xiaomei's paper. She's in our research group, to actually mine these genomes and look for these types of extracellular electron transport pathways that will tell us, hopefully, that yes, you are right, we are lithotrophs. So this is ongoing work that I'm trying to do right now. It's kind of hard to get a lot of good, high-quality genomic DNA out of something that's loaded up with kaolinite and iron oxide and is low biomass to begin with. So here's hoping. All right. So some conclusions, and in the interest of time, I'm still working on it. And thank you, especially NASA, NSF and the CZO program, and my collaborators. And I'll take any questions.
Questions for Stephanie?
So I'm just curious, the enzymatic attack is contributing to the fast weathering, correct?
That's the
idea?
Idea, yes.
Okay, but they're growing extremely slow.
So
how do you reconcile that?
So this is based on, on geologic time. I mean, so I'm growing in 50 grams, right? Mm-hmm. But you have, I don't know what the volumetric equivalent or what it would be on this Pluton. I have no idea volumetrically how big it is. But if they turn over, if there's a lot of them and they turn over maybe once a month or even once every 2 weeks, which lithotrophs are slow growers, it's not entirely unreasonable. And I've also just kind of at a first pass level done a little bit of like reactive transport modeling, and based on like just general dissolution rates, I have to do something very crazy that I just don't think is geologically appropriate to actually try to fit a match to the observed weathering rate we see here. So we don't unfortunately have a number we can plug in. There's no iron oxidizing, like go this fast to throw into a model, unfortunately. So.
Quick follow-up. So are there like biofilms growing on the surfaces of the rocks? Like what's the biomass like?
Some of the other work that I didn't show here is there's halloysite nanotubules there. There's microbes. You can see cells associated with the mineral phases. But in the interest of time, I didn't drag you through all of the background information. So you got one back there.
Does an increase of lithotrophy, of mineral consumption mean an increase of microbe production?
So an increase in lithotrophy And then an increase in cells, is that?
So that's the question. Basically, meaning if there's more of an iron source, does that mean there'll be more microbes?
Yeah,
per se?
so just simple free energy, right? So if you have more iron to oxidize, you can build more cells. Just at the most basic thermodynamic level, then yes, that would be true.
Okay, let's move on to the next talk. Let's thank Stephanie once more.